Hi, thank you. Okay. So I'm going to begin my talk discussing how we define imagination in this study. Imagination is an internal simulation of stimuli or events that can influence arousal, affect, and cognition. And we know that imagination has real-world effects on behavior, dating back to the studies by Shepard and Metzler on mental rotation in the 70s. Importantly, imagination actually activates modality-specific sensory cortices. So, for example, if you're imagining an image, there's activity in primary visual cortex. Imagination also induces cortical plasticity in sensory cortices and possibly other regions. For example, in the study by Pascal Leone, they showed that physical practice of playing a piano, so moving your fingers while playing the piano, expands cortical representations of the fingers in the motor cortex through time as you practice. But equally, this happens if you just mentally practice moving your fingers without actually moving your hand. And compared to a control condition here where there's no practice, you don't see that change. Okay. So for these reasons, imagination is a unique and useful emotion regulation tool, and it underlies what's known as imaginal exposure therapy. However, very little is known about the mechanisms or the effectiveness of imaginal exposure therapy. So imaginal exposure therapy is rooted in Pavlovian threat conditioning, so I'm just going to give a brief overview of this. This is when you take a neutral tone or a neutral stimulus, such as a tone, that elicits no real response from a person, and then pair it with something intrinsically aversive, like an electric shock, and then upon subsequent exposure to the tone alone, you elicit a conditioned threat response. For example, here, skin conductance threat-related physiology is plotted. And this type of learning is dependent upon the amygdala. Sensory input is integrated there, and then it outputs the brainstem and hypothalamus, which then controls your physiological threat response. Threat extinction learning is then when you are re-exposed to those tones without the intrinsically aversive stimulus, and then you can create a new memory that suppresses the original threat memory and reduces your threat responding. And so this type of learning involves a wider network. It involves the hippocampus, which integrates contextual information about the extinction context. And then in order to activate the extinction memory later, the VMPFC will integrate information from the hippocampus about the context of extinction, and if it determines that it's in the extinction context, it will activate inhibitory cells in the amygdala, and then that would suppress the activation of the physiological response. Okay. So imaginal exposure therapy in our question here really questions the role of sensory input here. Do you actually need to be exposed to the real world stimulus in order to activate this network, or can you tap into this network simply by imagining exposures to these stimuli? Okay. So in order to test this, we bring all our participants into the scanner and we have them undergo a threat acquisition paradigm, so very similar to what I just described. They hear a tone that is paired with shock 33% of the time, that's the CS+, and then another tone, the CS-, is never paired with shock and thereby predicts safety. We recorded skin conductance as well as took brain images. Then the subjects are divided into one of three groups. The first group is the group of interest, and so this is the imagined extinction group, and they're cued to imagine those tones that they just heard repeatedly, and they receive no shocks. And then there's a real extinction group as a control, and they hear the tones repeatedly without shock. And then there's another control group called no extinction or none here, and they're cued to imagine two neutral sounds from nature, either birds singing or rain falling. They imagine them both. And the purpose of this is to control for just the relaxing and internal properties of imagination. Importantly, they're not getting any exposure to the tones here, so they shouldn't be creating any new learning related to the initial paradigm. And then all participants are then re-exposed to shocks in a reinstatement period. So importantly, there's no tones here. They're just reminded that they're in a dangerous context by getting 4 unsignaled shocks. And then after this, they undergo a re-extinction phase where they are re-exposed to the tones that they heard originally, and then we can look at their level of threat expression. So importantly, after reinstatement, everybody should recover some fear, but if they did make an extinction memory during the extinction sessions, then that should be retrieved throughout this session, and towards the end of the re-extinction period, they should have no threat responding. So that's what we hypothesize, that the imagined and real extinction group will not show threat at the end of the re-extinction period, while the no condition or none will. And so this is the period that we test for the effectiveness. In order to test to see if threat was recovered in the brain, we decided to create a neural threat signature that was predictive of threat in this study. So to do that, we trained a support vector machine classifier. It was linear to predict the CS plus and the CS minus during the acquisition trials on the unreinforced CS plus trials. So this is the predictive weight map. After we bootstrap and threshold the predictive weights across the brain, we find that the brain regions that are most predictive of threat are very consistent with the literature in the univariate. So we see that the PFC, the periaquedural gray, bilateral amygdala, as well as parts of the basal ganglia and the insula are activated in the dorsal anterior cingulate. And this threat signature has a classification accuracy of 77%. This was done doing a leave 3 subject out cross-validation procedure where we left out one subject from each of the different groups in order to just control if there was any bias. Importantly, this signature was recently validated in an independent data set by Zhao and colleagues. It's available online, so if you're interested in this, just reach out. Then we take this classifier weight map, unthresholded, and then we apply it to the contrast maps during the late extinction for the CS plus versus CS minus across the different groups by just taking the dot product between the two brain activity maps. And then we look at what's called threat pattern expression in this study to test if there's a recovery of threat. So we find that the no extinction group is the only group that's showing a positive threat pattern expression. So that indicates that they are showing threat responses towards the end, while the imagined and the real extinction groups are not, indicating they extinguish the threat response. We also see the same pattern in the threat-related physiology. And importantly, the threat-related physiology was correlated with the pattern expression. Okay. So imagined extinction worked in this study, but how? In order to answer this, we did a functional connectivity analysis with no contrast across the entire extinction session. It was constrained by a priori ROIs that are related to threat learning. We find that the networks that come out are each unique, they're distinct, so they're all different processes, but there are some interesting similarities. And just to walk you through this, links here are only plotted if the partial correlation between nodes survives FDR correction. Shorter links indicate greater connectivity. And node side is related to betweenness centrality. And so just for the interest of time, I'm just going to point out one interesting aspect of this, and that's that the VMPFC has a significantly high betweenness centrality in the imagined and the real extinction groups as relative to the no extinction group. So it indicates that, like real extinction, the VMPFC is a central hub to the neural network supporting imagined extinction. Okay. And if we extract a signal from the VMPFC in a univariate analysis and look at its activation to the CS plus relative to the CS minus, throughout all the phases, we see that there's an increase in VMPFC activation in both the real and imagined extinction groups, and this is something you would expect from real extinction. So it's interesting to see that both processes are doing this. And then if you just take out the spatial pattern during this peak period of activity, you find that the spatial correlations are higher between the imagined and real extinction groups. So they're not doing exactly the same thing, but they're more similar than compared to the no extinction group. And then also interestingly, activity during that period in the VMPFC predicts extinction success. Extinction success was defined here as the threat pattern expression in that late period, so related to the first figure I showed you. So if they reduce their threat expression, that's considered extinction success here. Okay. And relatedly, the amygdala and the auditory cortex were also predictive of imagined and real extinction success. And importantly, these regions are not predictive of threat expression or extinction success in the no extinction group. And then to look at what's unique about these, the nucleus accumbens uniquely predicted imagined extinction success, but did not predict extinction success in the real extinction group. while the hippocampus did predict extinction success in the real extinction group. So it's interesting here, and we interpret this that imagination is updating a value signal related to the percept of the tone, and that there's probably a lot of individual variability there. Okay, so a result summary. Imagined extinction reduced neural and physiological condition threat responses. Activity in the VMPFC, auditory cortex, and amygdala is related to imagined and real extinction success. And the nucleus accumbens uniquely predicts the success of imagined extinction. So the takeaway here is that deliberate imagination can attenuate threat responses through perceptual and associative learning mechanisms that are supported by the VMPFC, the auditory cortex, amygdala, and the nucleus accumbens. Thank you. If you're interested, this paper came out in the fall of last year, and I have a poster on this today if you'd like to talk more. So I'd like to thank my former advisor, Tor Wager, and Daniela Schiller, and my former lab at the Cognitive Effective Neuroscience Lab at CU Boulder. Thank you.